Okay, welcome everyone. Today, Zach is going to talk about deep learning as program synthesis. Take it away.
Yeah, thanks, Ron. Today I'm going to talk about um, how deep learning might be performing a form of program synthesis. Now, this isn't, I think, necessarily a novel hypothesis. At least there's a lot of things which are kind of quite people have said which are quite close to this, but I'm aiming for this to be a sort of synthesis which really brings together a lot of evidence um, and frames things in a particular way so as to lead to specific research questions. I'm going to lead up to some particular mysteries that you need to solve if you want to make this work. And uh, they're not chosen by accident. So this is all sort of leading up to, I think, a particular research agenda. Um, So, yeah, that is to say, all the good ideas here are other people's, and the bad ideas are mine. Um, so, yeah, with that being said, I'll get started. Um, okay, so as everyone here, I think quite likely knows, we are living in a world that is now full of um, deep learning and AI everywhere from scientific applications in AlphaFold to Sora 2 just came out like yesterday. Some crazy videos. Um, ChatGPT, IMO Gold for Gemini and ChatGPT, I think. Um, so yeah, this is not where very few people predicted that would be anywhere close to something like this even 5 years ago. I will say there were the people who came the closest. If you ask them what they think why we got here, they might give you an answer like this. So here's from the GPT 4.5 launch discussion. Sam Altman, the CEO of OpenAI, asked one of his researchers in this discussion why does unsupervised learning work? And he says um, essentially Solomon induction. And he proceeds to explain what Solomon induction is. This is a form of program synthesis or universal induction. Um, and um, so what you find actually is this belief in program synthesis and the sort of it kind of runs quite deep among the people who really the original people at DeepMind at OpenAI who really believed in scaling that this would work because scaling at the time, it seems like a completely naive belief that you could just like throw resources at the problem and um, it would just magically improve without any additional human input. But if you believe in a story like this, it no longer becomes so surprising. So Shane Legg, who founded DeepMind, his entire PhD thesis uh, was on Solomon induction and IPSY, which is uh, where you add reinforcement learning to this. Um, and this is what I think motivated people. As you can tell from the title of the thesis, these ideas were often originally inspired by like what would AGI look like ideally before we even had AGI. Um, and so I'm uh, here to claim that deep learning is already sort of doing something like this. Um, uh, okay, so I'm going to yeah, I'll go through what I'm going to talk about today. Um, and so first, I'm just going to review what is program synthesis, what's the background here. Now, the sense in which I use program synthesis is going to be rather loose, as I'll discuss. Um, Although at the end, I'll come back to how you make this a little more precise. Um, but I want to talk about where these ideas are coming from first. Then I'm going to introduce my claim, what I mean by programs, and what I mean by program synthesis. I'll discuss what I think the strongest, most direct evidence is we find programs, things that look quite clearly like programs in specific cases when we do interpretability. Now, the problem is, uh, well, you don't find these all the time. So why are these not just special cases? Why is this the general case? I'm going to explain um, why I think that it's um, not surprising that interpretability doesn't find everything all the time. And then I'm going to discuss, because we can't use this direct evidence that, if MEC interpreters showed uh, the programs for every single deep learning model, I wouldn't have to give this talk. So I'm going to go through, because we don't have that, I'm going to go through the indirect evidence, which I think it's almost weirdly consistent with some very otherwise surprising kind of paradoxes about um, deep learning, which I'll go through. Um, and then at the very end, throughout this talk, you may get some like nagging feeling like, oh, this would be cool, but like this, how do these two things work? Like, what do you program? What do you mean exactly by program? And like, well, isn't, Solomon induction super inefficient, blah, blah, blah. Keep those thoughts in your head. I'm deliberately focusing attention to these problems because I think that's a productive direction for research. Okay, so let's get started. So background, where is this programs and this idea is coming from? I mentioned they're very old and deep. Well, of course, Turing originally came up with the idea of Turing machines. Very quickly, the community uh, realized that Turing machines were not just like one way to compute things, but actually pretty much any way you can think of to compute things ends up being equivalent to Turing machines. So there really is some universal sense of computation. That's this Church-Turing hypothesis. And later on, people like David Deutsch and Stephen Wolfram added on this physical Church-Turing hypothesis that the laws of physics actually are described by something like a Turing machine, or you can approximate them to arbitrary accuracy with a Turing machine. This is what I think leads to the idea that something like program synthesis might be possible. If physics is actually, if anything in the real world is generated by a program, then all you have to do to figure out what generated some observations is find out what program generated the observations. Just reverse the process. If a program generates observations, then take those observations and turn them into a program. The problem with this is there are a lot of programs. And it's hard to figure out which ones to pick. So there's this old idea of Occam's razor that you should pick simpler things, and Kolmogorov complexity formalizes this as shorter programs. So you pick programs with a shorter length, and then Solomonoff induction takes this idea and says um, put higher prior weight. It's a Bayesian um, learning algorithm, put higher weight on um, programs with um, lower Kolmogorov complexity. So you search over all possible programs, you put you put higher weight on ones that are simpler, that have shorter programs. Um, and finally, AIXI adds reinforcement learning to this to make it actually pursue goals. Um, uh, and so yeah, this is a very old ideas about like what is the optimal learning algorithm, right? It's Bayesian, it's searching over all possible programs, and it's weighting it by program length, by simplicity. Um, Now, this is really great in theory, but as I'm going to come back to at the end of the talk, well, Solomon induction is incomputable, and then there are approximations to it, like speed induction, but they're super inefficient. Um, and so this was as great as theory, but never been clear that this could really be instantiated in in the real world. Um, okay, so now I'm going to get to my claim. So it said deep learning is performing a version of program synthesis. And when I say this, I mean this in a slightly looser sense of the word program. So this doesn't mean like Boolean circuits or Turing machines or something like this. I mean that you're composing reusable parts where each part is fairly small. It does a specific small fixed rule with only a few inputs. Um, and then you get the aggregate behavior by wiring all these parts together. So if you think of like a Boolean circuit or something, you have gates and you wire the gates together. You get the total behavior. Turing machine, you're like wiring together these step functions, head movements, and things like this. Um, but this also applies to things that you wouldn't normally fit into. This also applies to more general forms of computation, arithmetic circuits, so like polynomials in terms of feeding together multiplications and additions, but also uh, also like function composition of um, uh, n array functions, which are continuous. Um, so I mean this in a pretty general way, but yeah, I will come back to this question of making things more precise because there are some subtle issues uh, here. And then by program synthesis, I mean you could say, oh, linear regression is just program synthesis. I just need to like fill in these numbers here, which are the slope and intercept uh, of my data, and I've synthesized a program which reproduces my data. So no, what I mean is general purpose program synthesis, general purpose program search. So not just a relatively limited class, but a fairly broad one. And I'm going to say almost any efficient program. And again, there's a lot of complexity hidden um, in that statement. You could think of it for now as something like polynomial time minus pseudo-random stuff, but this is a bit subtle. And then I mentioned that this simplicity bias. I think a corollary of this is that to perform well, you do need strong inductive biases like simplicity bias. It's not enough if you really are searching from such a large space of possible hypotheses. You need strong inductive biases to make this efficient. Okay, that's the claim. And then the rest of this talk, for the most part, is just going to be me giving evidence. So I think the most direct evidence comes from mechanistic interpretability, from the fact that when we open up a lot of these models, we actually do see programs, what we would call programs. So there's this great paper, I'm sure a lot of people are familiar on grokking modular addition, that if you train machine learning models, if you train a shallow um, uh, MLP or transformer, some papers they've done both to learn this modular addition task um, of uh, uh, then what it ends up actually yeah, it might have been it's modular yeah um, then it actually learns this quite sophisticated algorithm for it using a trigonometry. So it actually will add these things sort of by encoding them um, in this Fourier basis um, via these sort of angles and kind of adding them. You can actually see this as a representation theoretic algorithm for solving this problem, which there are actual follow-ups that show that it does learn these kind of more general representation theoretic algorithms. So it's doing something I think pretty non-trivial and in an interpretable way. It's actually using this uh, Fourier structure to add these numbers. Um, this is I think, a pretty classic example. Even older example, which demonstrates the kind of compositionality I'm talking about. This is Chris Olah and his group's old work on vision circuits. Um, so it turns out that if you go through these convolutional neural networks that are learning to classify images, right? Obviously, they're going to know like if you ask them to classify like different types of cars or cats or something, they're going to know just by the training objective, what those different things are. You train them to do that. But what's surprising is that the internals actually learn human interpretable stuff as well. So you get like car body detectors, window detectors, wheel detectors, and then they assemble hierarchically. So you actually get a car detector, um, which which looks and sees if the windows and the car body and the wheels are in the right place from the previous layer, and then assembles those to build this car detector. So you get just like in circuits in classical computation, you get these sort of soft kind of analog circuits that are composing together these smaller solutions to build larger and larger. So right here, I've showed one step of the process that the car detector is assembled from Windows car body wheels, but those themselves are assembled from shape detectors, which are themselves, from assembled from curve detectors, etc. So it's all compositional. This is sort of much like how programs in classical computation work. Okay, so as I mentioned, yeah, it's not so fast. Um, okay, yeah, deep learning learns algorithms. It learns learning something like programs in these specific cases. Um, that's, I think, fairly convincing. But is this really happening in general? Um, And even worse is like, suppose that this is happening in general, then isn't shouldn't these same tools show us this? Shouldn't we just be able to open up these models and immediately see that they're doing um, that they're learning these kinds of programs? And yeah, spoiler, they don't. Uh, that's um, there's there's a lot more examples than the two I showed, but it's still, if you take just some random neural network that you trained, you're going to have a hard time uh, getting results this clean. So why is this not a big piece of counter evidence, and why we keep going here? And basically, my answer here is, who says it has to be that easy? Um, right? Uh, there's no reason why, even if this is made of small, understandable compositional pieces, that like it has to be in this particular neuron or something. Like, ah, yes, there's a grammon neuron, and there's a, just like you get in the CNN. Why does it have to be that clean? You could have a very much more complicated mapping here. Like an example, for instance, is how we actually construct computers, which like our software has very compositional structure. You have subroutines. I mean, it is, software has program structure. I mean, that's sort of almost definitionally. Um, and yet, if you tried to go and like probe transistors and figure out like which ones are responsible for different things, which this is on the right hand side. This is a really great paper. Could a neuroscientist understand a microprocessor? And you have a computer which is playing like one of like Donkey Kong, Space Invaders, and Pitfall, these Atari games. And you try and like use neuroscience techniques. Like right here is lesioning. So you're saying like, if I delete specific transistors, can I figure out which transistors are like responsible for the Donkey Kong behavior versus the Space Invaders behavior, etc. And obviously this is kind of like naive. There are no like Donkey Kong transistors or whatever. The abstraction level where things are happening is different. And this is just sort of what happens by default. What I'd argue is this is what happens by default in an information processing system where you don't know how it's organized, is there may be non-trivial kind of units of organization, the sort of atoms or cells, um, but they're not necessarily going to be spatially localized where you expect to look. And this is also something we see empirically in polysemanticity. This is well known among interpretability folks in some version. So the whole point of this is to say uh, we can't do it right now, but that doesn't mean we can't do it ever. And that doesn't, I think, mean that this is it's not, in my opinion, surprising that these techniques don't work all the time. They work when the network it has constraints such that the structure surfaces itself. Like in a CNN, sparsity means that you can't choose a really wonky representation because it has to localize, for instance. So uh okay, that brings me to okay, if we if we knew what the right place was to look, then we'd have just completely solved this problem. But we don't exactly yet. People are working on that. So then now I'm going to talk about what evidence can we leverage in the general case. So um, I've argued that this is the fact that we don't that MEC doesn't work all the time. It shouldn't be counter evidence here, but I still need to argue that um, that this program structure shows up that this explains things more generally than just these specific examples. And there we go. The way I'm going to do this is I'm going to discuss three paradoxes um, that I see in uh, that people have pointed out in deep learning and explain um, why they make sense under this hypothesis in a way that they don't they didn't otherwise. So the first one I'm going to start with is approximation. Um, so this is like the first question that you ask about a neural network. Uh, I mean, we've created a system to learn things. We take a task and we ask a neural network to learn this task. Um, and there's all these questions about like, well, you know, can it learn it from only some finite number of samples, or can it practically find a way to that solution, blah, blah, blah. But before all of those questions, there's a much more fundamental question, which is there even some neural network, some parameter which actually performs well in that task? Like, who's to say that like it could just be that all of them perform badly? Um, uh, so there's a classic answer to this, the universal approximation theorem. You might have heard of this. That they teach it in a lot of classes, um, and it's somewhat of an open secret that the universal approximation theorem is kind of bullshit, which is because uh, it turns out universal approximation theorem is just like Stone-Weierstrass theorem from analysis. It applies to like polynomials, to uh, sine functions, to wavelets, whatever. Uh, it's it's literally just if you look at the construction. I guess I should back up and say um, the real crux is so what universal approximation theorem says is you can approximate any sufficiently smooth function with if given enough neurons, with a neural network that has enough neurons. The problem is enough neurons turns out to be exponentially many. The construction requires exponentially many neurons in the input dimension. Um, and again, if you're familiar with classical computer science, that's precisely what like a lookup table requires, right? Like a lookup table of D inputs, and say binary inputs is going to require 2 to the D bits to describe that um, lookup table. And if you look at the construction of how the universal approximation theorem actually works, it's like constructing a continuous version of a lookup table. It's like literally interpolating. Um, so this is not an explanation. Um, okay, so then what? So now we're left actually with this problem called the cursive dimensionality. This is a big um, subfield in deep learning theory. Why is it even possible to avoid this problem of in high dimensions? It's super hard to learn these functions. There are like exponentially many. There's for instance Boolean functions. There are 2 to the 2 to the D Boolean functions on D inputs. That's a lot of functions. And so how could we possibly be be uh, be able to learn that with only a very small amount of space? Um, and well, my answer here is that, and this is not just my answer, but there are other people, namely, for instance, Tommaso Poggio has this similar answer, which is that this is actually not a new problem. This is the exact same thing we face in computer science, which is like, well, we want to learn a problem, but writing a lookup table that specifies every possible output for every possible input would take way too much space. So instead, you have to break the problem down into sub-steps, small enough until, the sub-steps are small enough that you can memorize them. Like a gate is just a lookup table, like an AND gate just memorizes what you do on uh, two inputs. So you get this exact same problem. Arbitrary Boolean functions require exponentially many resources, but there's a ton of real-world problems that only require polynomially many. And that's what saves us. Real-world problems, like for instance, I got on the right there, I've got addition. Addition, you can break down adding 2 plus 3 plus 4 into adding 2 plus 3 and then adding 5 plus 4. Um, Problems break down. And this is actually, I think, a core point I wanted to make. This is an inherent in my definition of what a program is, but I think this is core to basically this is, in my opinion, sort of what programs are, is breaking down problems hierarchically into smaller programs. I think this is essentially the core of um, computation in my view. Um, and it goes actually even a little bit further. There's these depth separation results. It's not just that you get have this one vague parallel, but there's actually further. Turns out that this hierarchical problem solving isn't just useful, that there's theorems that say it's necessary. These actually directly parallel theorems that you get in Boolean circuits, um, which is that there actually exist functions which require exponentially many neurons um, for a shallow net to implement, but only polynomially many for a deep net. So there are some functions which are sort of like intrinsically deep. They can't be flattened into a shallow neural network. Um, and this is sort of what you'd expect again from classical computation. Like there are some functions which are some problems which are inherently sequential, inherently serial. You can't just flatten them into a big shallow circuit that it does everything. So this is a really clear parallel. These theorems kind of directly um, sort of line up. Um, then I'm going to talk about generalization. Uh, so this, I think, directly ties into, I talked a little bit about scaling before, like why did they make this bet that you could make neural networks bigger and bigger, and then this would just work. Um, because not only is that like crazy to think that it seems kind of like a naive thought, but it's actually actively counter-predicted by the classical statistical learning theory. If you think of a neural network as just like a normal statistical model, the sort of default view, then this is actively the success of just naive scaling is actively counter-predicted by uh, the classical theory, which says that learning is about balancing overfitting and underfitting. That if you have um, too much, if you make your model class too complex, if you give it too many parameters, you're just going to overfit and learn this super wiggly line that just passes through all your data points. And if you don't give enough parameters, you'll underfit. And so there's some Goldilocks zone of choosing the complexity of your model class just right. It's a um, it's a very like human design choice that what's the Goldilocks zone? What further, there's things like no free lunch, which tells you that actually it's this further this human design choice in choosing the priors to match the problem, that there's no universally good um, learning algorithm, only ones which are adapted for different domains, and humans have to choose this. So big emphasis on the classical theory is human choice. There's careful Goldilocks zones and things like that. Thing you would never do is just like crank up the scale and hope it's generalized. Um, it turns out this actually works fine. So here I've got plotted something known as double descent. Now I don't want you to get the impression that this is like what happens all the time. That's sometimes misstated, but it does show that this naive theory isn't quite right, because what the naive theory would say is that there's one valley. As you increase your model complexity, the generalization hits this Goldilocks zone, and it's just this thing with one valley. But here you have a valley, and then at some point it goes the other direction. The classical theory would never predict this. Um, that actually adding more parameters could help generalization. And the thing is, this is not that surprising if you believe that deep learning is doing something like program synthesis with strong inductive biases like simplicity bias. Well, this is not that surprising. Like a Solomon induction, um, it doesn't matter like how much as you give it more resources, it will sort of just do better. Um, uh,
Wait, I have a question.
yeah,
Is this graph made with the same amount of data for like all the data points?
draft,
Like this graph is every point for
graph.
everything on the x-axis, like the same amount of data, but just like more width, more parameters.
Yeah, I think so. Yeah, I think I got this
Mhm.
from OpenAI, but yeah, I'd have to remember.
Mhm.
Yeah. So yeah, what you'd expect is for the same fixed data set that more parameters would eventually be worse. Um,
Yeah.
yeah, so this is called double descent if you want to look it up. Um, um, but yeah, people make it out like this is the modern this is like the modern way generalization behaves. This is actually you only get this double descent in specific cases, but it's enough to show uh like like uh like this shows a non-monotonic relationship uh between parameter counted generalization, which is enough to show, your classical theory seems like it might not work like you think it does. Um, uh, and so this makes complete sense under um, if you're doing something like Solomon induction. The fact that you have a simplicity prior means that if you expand your hypothesis class, like if I'm performing program search for programs with a hard bound, programs can't be larger than 100 uh, 100 squares. Um, and then I lift that cap to 200. I'm not going to hurt my generalization that much because my Solomonoff prior was already down weighting those complex programs anyway. Um, so I can kind of get that extra expressivity for relatively little cost because um, my prior is good. So that wouldn't be too surprising. Um, there's other phenomena like data dependent generalization. Actually, I realized I should have added a slide for this, but a big thing that surprised people was that there's a paper, Understanding Deep Learning Requires Rethinking Generalization, it's a fairly famous paper, um, where they show that you can train a neural network on the same network, same exact network on white noise, um, train it on white noise. Then I have another training one where you train it on real images. It's like an image classifier. You train it on real images versus white noise. Um, and in the white noise case, it of course completely memorizes the data, generalizes terribly. In the real images case, it generalizes quite well. It's very low gap between test and train loss, which is super surprising that you could have this super strong data dependent generalization effect. This doesn't happen if your model class is very uniform, as kind of classical statistical learning theory usually expects. But if you're actually searching over something like programs, which have a lot of structure, well, of course, if your hypothesis class includes both programs that are very short and programs that are very long in the same hypothesis class, then they can generalize very differently. So if my training data leads me to a very short program, then I can have low generalization error. But if my training data forces me against my prior to learn uh, a really long program, then I can generalize poorly. That's not too surprising from this perspective, but it was very surprising when this paper came out. Um, and I'll make a final comment, which is this story about generalization and mechanistic interpretability is actually not so separate. So I mentioned that grokking, that the modular addition example before. Well, actually, if you look at it over training time, you'll find there's a big jump in the generalization performance of the network. The test accuracy has um, this steep cliff. Um, and it turns out if you look at what happens right before and after that cliff, it turns out that it's actually proceeded to learn this Fourier-based algorithm for modular addition. So this jump in generalization didn't just happen accidentally. It was due precisely to this circuit developing. It's not, at least in this case, it's pretty clear these are the same story. Um, uh, okay. And then I'm now on to, I think, yeah, my last paradox, which is convergence. So uh, yeah, I'll just leap right into it, which is that uh, like a priori, every trained model is its own special snowflake. Uh, even if I have the same architecture, whatever, initialization is going to drop me off in some random location, and then I'm going to train on my loss. But the loss landscape is like super non-convex, and many different minima, whatever. So it's like I really wouldn't expect to end up in the same place at all. Um, Especially if I have different architectures. If I have a different architecture, there's absolutely no reason why you would have similar behavior across different architectures at all. And yet, despite this, well, we have a lot of evidence that there is this convergence across a lot of architectures. In particular, I'll mention representational alignment. So this is a really big subfield. There's a few reviews that you can check out that cover a lot of this stuff. Actually, yeah, in AI as well as neuroscience. But so this shows up across different training seeds. You get alignment even across different architectures. You get representational alignment. Even often, sometimes over the entire course of training, you'll get alignment of the function space trajectories of these models ends up being aligned. And even the alignment here is so strong that you can often just like zero shot stitch models together. I can take two different models trained in different ways or whatever, and like stitch them together with a really um, a really just like a linear adapter sometimes, um, or occasionally like um, no adapting. Um, this is yeah kind of surprising from like you'd never expect to like uh, take like a um, some like random forest or something and like be able to like cut off one and take another one and like stitch them together and have this just work naively. Um, and one little tidbit that I can't resist mentioning it opens a whole little rabbit hole, but I'll just mention it, which is that we have pretty decent evidence that AI models share similar representations to human and animal brains, like Gabor filters and vision. Um, there are whole reviews on this. There's a lot of ways in which human and AI representations align. Now, what that implies about, if this hypothesis about AI models is true, what that implies about human brains, I'll leave up to you. I won't speculate there. But um, yeah, this is all totally explainable from perspective of deep learning being something like program synthesis. Again, I mentioned this physical Church-Turing hypothesis, the target that data comes from the real world, is generated by a computable process, i.e. physics. Um, then any general program synthesis algorithm is going to eventually find that computable process, or more realistically, some projection or approximation of that process. It's not like literally learning uh, QFT most of the time. Um, so yeah, and then there's this paper, the Platonic representation hypothesis, which has I think made some waves recently, which discusses that, like for instance, image models and text models um, describing the same data in very different ways will develop similar representations that, and that's because you're learning the same projections of real world structure. Um, but yeah, there's a whole lot more you could say about. I mean, it's very non-trivial, the idea that there's real structure in the data distribution, structure in coming from physics, from the real world. So I don't want to kind of undersell that, but I'll kind of move on for now. And I mentioned I'm going to come back to scaling again. The bitter lesson, half so I can just share this meme uh, uh, from Ilya Sutskever. Um, but yeah, so we used to have all these different subfields, computer vision, natural language processing, all these different areas. Now it's all just big transformers. Uh, to I think the disappointment of a lot of people. Uh, and well, the explanation here is, well, if deep learning is already performing something like general program search, it doesn't need any help, any hand holding. That if you encode human priors in the architecture, you might get short-term gains, but in the long term, it'll be, best useless or at worst actively hamstring um, the model with the constraints you put on it. So this is an explanation for Sutton's bitter bitter lesson. And yeah, and then I'd say this maybe could be its own paradox or something, but I've kind of shoehorned it in here. That actually you not only do you that I think a really surprising thing about these representations that you develop um, is how they can extrapolate or what people might call out of distribution generalization, although that's different from the sense of generalization that I talked about earlier. But uh, like the clearest example, for instance, is transfer learning. So you can take an LLM which is trained on 99.9% English data and a tiny fraction of French data, and it performs substantially better on tasks in French than you would expect a model that was only trained on that amount of French to be. And the reason being that it's learning the world model, the reasoning patterns, everything from English, and then just uh, learning how to represent those in French. Um, and actually, the paper that I cited here, what's funny is this kind of happens by accident. It turns out that if you train you think that, wow, these LLMs have these remarkable zero-shot translation uh, uh, properties when trained on only English data. But actually, it turns out that you like couldn't totally scrub all the French data or whatever out of your data set. And even that small fraction which is in the data set is enough to teach it how to speak French, which would surprise you because, well, that wouldn't be enough to teach it French on its own. But because it's already learned its world model and stuff from English, it can generalize to French. Um, there's also, yeah, transfer learning based on retraining that you can fine tune that the classic paradigm is fine tuning that the original this is why large language models are called like pre-trained models because the idea was that you would take a large language model, you would pre-train it, you'd train it to develop world models on using English data, and then you'd fine-tune it on your specific use case. Um, and that knowledge would transfer. Um, and again, and of course, this paradigm is now itself overshadowed by in-context learning. That idea is actually you don't even need to fine-tune, just prompt it and it will generalize zero shot in context. It will just you can just tell it in English what you want it to do, and it will generalize to that at runtime. Both of these are pretty surprising, I think. a priori, but from this program synthesis hypothesis, well, the entire point of programs is that they reuse those pieces that they have, right? You have subroutines and pieces that you reuse and you compose. So in particular, like in context learning, you view as, from this perspective, it'd be composing learned components at runtime. So like SQL is an example in classical computer science that I take some input string and then I um, can can take the little bits of that input string and say, okay, this refers to this table, and I want to do this operation on this table, and I want to insert like this string or whatever into this table, and you just compose these hypotheses, these subroutines kind of at runtime dynamically. That would explain what's going on here. Um, um, and yeah, well, there's a lot. I think there's a lot more I could say, but I've sort of already, I think, gone in a bit of detail into how the various evidence here. Now I want to return to this question that I mentioned a couple times at the beginning, that there are specific kind of rough spots here, specific mysteries to turn this from a kind of hand wavy uh, correspondence to something more precise. Um, and I'm picking these two mysteries. I call them mysteries, but I actually have very strong opinions about them. Um, and it's sort of out of scope for me to kind of discuss um, precisely what I think the right kind of answers to these are. Um, but I want to point in this specific direction because I think they're productive ways of framing questions. So I'm going to say there's two problems here. First one is what I'm going to call the type mismatch problem. So how do we even make sense of this notion of like neural networks learning programs in a coherent way? Like this doesn't quite make sense. Like programs are these very discrete objects, and discrete not just in terms of like you can have analog computation, like so it's not just in terms of the values like ones and zeros, but the fact that you have this graph, this compositional kind of graph structure that's very discrete thing. And neural networks are fundamentally continuous. They're in far more geometric objects than discrete ones. These are kind of two very separate worlds. Um, and I mentioned this sort of interpretability problem at the very beginning. Well, this is, I think, necessary to even make sense of this. What programs? What are we trying to find? Um, I think you need to square this circle. Um, and uh, the second thing I'm going to highlight, I mentioned this also at the beginning, um, this learning problem. Um, I mentioned that Solomon-Off induction is incomputable. These more tractable versions are still super slow. So, uh, how are neural networks doing this? Right? And we have some hint, right? SGD works really differently than like Solomon-Off induction or speed induction, which those will just brute force. They'll look at every possible program and see how it fits the data, which is super inefficient. Um, SGD is doing something that looks a lot more greedy. It's locally probing information and figuring out where to go. And this is a pretty classic question in optimization theory. Why do you get global convergence from SGD? And I'm going to frame it in a particular way here, which I think is productive, is that you need local global correspondence. So you need that this local gradient information leads to global trajectories that arrive at the target function, ideally with this bias towards simplicity. Um, so um, yeah, I mentioned a little bit about geometry, this sort of framing of neural networks as having geometry here. If you really take that seriously, there is, um, yeah, there this yeah asking questions in this way about how does local structure constrain global structure. Um, that I think, yeah, I won't. I promised I wouldn't go off into my own thoughts as to how to answer these questions here. But how local structure constrains global structure, that's a pretty standard question in mathematics in fields like algebraic geometry, sheet theory. Um, but yeah, I'll leave it there, and I will really quickly just recap the whole talk. Um, so uh, my claim was that deep learning is performing a version of program synthesis, asterisk, asterisk, asterisk. There's some evidence from mechanistic interpretability, but that's not sufficient because there's only specific cases. So we need to go to this indirect evidence um, that there is. I talked about how can neural networks even represent, how can neural networks even possibly represent the target functions that we ask them to? Seems to require some kind of compositional structure. How can they generalize from finite samples to more samples? How come you get data-dependent generalization? How come you get uh, this generalization behavior, which seems to sometimes correlate with this mech-interp um, results? And then this paradox of convergence. Why do you get all these different models learning the same structure? Why does that structure enable transfer learning and in-context learning? And then finally, uh, I point to these specific mysteries of this type mismatch problem and the learning problem. So um, I really think that thinking hard about how how does program structure lead to more geometric structure that fits in with neural networks? This connection, I think, is a really um, productive direction. And then from this perspective, this learning problem, thinking about how local structure leads to global structure, I think that's um, productive. Um, and maybe I'll say very briefly that uh, while we haven't, I think, worked out the answers to these problems in full, I think we do. I won't discuss these in full, but I will say, for instance, this connection between discrete structure uh, um, and continuous this program structure and geometry. Yeah, I don't want to give you the impression that this is this is not something that this is a thing that many of my collaborators are actively thinking about. So in this very seminar, Dan Murfitt talked about geometry of this programs as singularities paper, which discusses basically what I'm talking about with this type mismatch problem. So in a very particular setting, you can make this bridge. Um, I have some in progress work on this learning problem issue, and there's a lot more thoughts that I think we have that are in progress. But I'll leave it at that.